Section 4.7, optimization problems. What this section is about, we are still using basically applications to derivatives. Everything we learned so far in this chapter is about applications to derivatives. And this is one of the other applications that we usually use, where we use derivatives with. Not just first derivative, could be second derivative and other derivatives. This section, optimization deals with minimizing or maximizing something. Could be like maximizing profit, minimizing revenue, minimizing cost, maximizing area, minimizing parameter. There's so many applications to this section. So almost all the questions they're gonna give it to us are gonna be in a word problem format. And so the first thing, these are the steps that I listed down here in an organized method. The first thing is always read and understand what that problem is about. What is the question about? What is it saying? Because a lot of times they read through it and then they start solving it without really comprehending what's within the content of the problem. So that's very important. Read and understand what the question. After that, draw a picture or diagram and label the variables. See what is missing, what I really need to work with, which areas I need to work with. Maybe these sides, maybe the base, maybe the height, maybe, I don't know, depending on the problem. So you label them with variables, X, Y, Z, A, B, C, whatever you like. And then write down what is given. Sometimes they give you area, sometimes they give you parameters, side length, sometimes they give you a relation between two things within the problem. Write it down so you know in front of you what is given and what is missing. State which variable or variables need to be minimized or maximized. That's what optimization is about, minimizing or maximizing. Then find the relation between the variables to set up, so you can set up an equation. So this usually sometimes we use the Pythagorean theorem or trigonometric equation, maybe like sine theta is opposite over the hypotenuse. Geometric formula like area, surface area, volume of a figure, they will specify for us which one is which. And then in some cases, very rare cases, we use the similar triangles. Similar triangles to get a relation between two variables. And then after we do this, we need to express the quantity that needs to be minimized or maximized. If it's area, we write it as A of X, volume V of X. So it says here, express the quantity being minimized or maximized in terms of a single variable. So in terms of a single variable. Differentiate the equation and find the critical points. Because we talk about minimum, maximum, that reminds us about differentiability, differentiation. So we differentiate it, set it equals 0 or does not exist, and find the critical points. Then we're gonna find the absolute min or max. From this point, when you find the min or max, we don't know, after you set the derivative equals 0, you need to make sure, and 99% of the time we're gonna be using the second derivative to check if the points or the critical numbers that we got are those for minimum or maximum. So the second derivative test will help us to see that. And then compute the remaining variable or variables if needed. So let's look at the first example here. Find the dimensions of a rectangle with a parameter of 80 meters and an area that is as large as possible. So it's a rectangle. So if I want to draw a rectangle, it says parameter, I don't know the dimensions here, so call them X and Y, XY. So that's the rectangle that we have, and an area that is as large as possible. So as large as possible, this means we're maximizing areas. So the area is maximized. Write that down. What they give us, the parameter is 80 meters. So we also write that down as well. Now we need to see how to start with this problem. Find the dimensions. So we need to find X and Y. They give us the parameter. Well, how do you find the parameter of the rectangle is you add all the sides up. 2x, 2y is 80. You can divide everything by 2 to make it simpler. So I got here something that probably I can use later on. So we read the problem, we assigned the variables, we wrote down the given, we wrote down what we're looking for. We need to find an equation now. Equation for the quantity that I'm trying to either minimize or maximize. Well, I'm trying to maximize the area. Okay, so what's the area of the rectangle? The area is always length times width. So the area of the rectangle here is x times y. So, but then they said write the quantity as a function in terms of one variable. So I'm not going to differentiate yet because I have two variables here. So what I can do, I can use that box equation and solve for y and get everything just in terms of x. And why did I do this? I can substitute it in there. So the area is x times 40 minus x. See, now I got a function in x. So the area is as a function in x. And we can clean up this by the distribution. So 40x minus x squared. So I get a function in x. What do I need to do with this? I would like to maximize it. Minimizing, maximizing reminds me of derivative. So I'm going to find the first derivative of this, which is 40 minus 2x. And what do I do with this? I set it equal to 0. So the first derivative equal to 0. And then I'm going to solve for x, adding 2x to both sides, divided by 2. So I get x equals 20. So right away, a lot of people, they just go ahead and say, okay, x is 20, substitute in and get the y value, because that's what I'm looking for, x and y. But you have to be careful here, because this number could be for, the critical number could be for min or max. So how do I verify this is really going to maximize the area of the circle, of the rectangle? So what do? We find the second derivative. From the first derivative, we get the second derivative, which is negative 2. Notice this is always less than 0 for all x. For all x, no matter what x is. So what does that mean? If the second derivative less than 0 means the graph concaves downward. The graph concaves downward. So we can say, so by the second derivative test, by the second derivative test, x equals 20. 20 is a local maximum. And in fact, it is also an absolute maximum. So that's the that's the x that will maximize it throughout all its interval or its domain. So it's also an absolute maximum. And why is that? Because I'm going to write it here. As we approach the endpoints, what happens to the area? The area decreases. But we're trying to maximize it. So that's why we don't have to worry about it. So at the end, I get x equals 20. 20 meters is the one of them, and the y is 40 minus x. So 40 minus 20, also 20. Notice, so the rectangle will be maximized when it's a square. When it's a square, because x and y are the same. The side lengths are the same. Now let's look at another example. So example 2, a metal open box, so there's no top, is to be constructed from a square sheet of metal that is 10 centimeters long. So it's a square sheet. Square pieces of the same size were cut from each corner of the sheet, and then the sides were folded up. What are the dimensions of the rectangle or the box with largest volume that can be constructed using this specific sheet? Okay, so what they give us? It's an open box. It's going to be constructed. So this is the sheet of paper, let's say, or metal, sorry. It's they said it's a square piece. It's 10 centimeters or long. So it's 10 centimeters long. Square pieces are cut. So let's say this is the one, and they are all the same. Assume each piece is x by x, x by x, x by x. And this would be 10 minus 2x. This would be 10 minus 2x, as you can see, because 10 and take away 2 pieces. When we fold it up, it give us it becomes like a box like this, an open box. So the height would be x. The height would be x. The base is 10 minus 2x, and also the other one 10 minus 2x. So this is the same as this, and this is the same as this, and the height is x. Okay, now no matter open boxes to be constructed from a square. I'm going back to read it again. A square piece of the same size were cut from the corners, and then they were folded, so we folded the sides up. Okay, so what are the dimensions? So they want the dimensions. So they want the side lengths, length, width, and height, the three of them. Of the box with largest volume, so we are maximizing the volume. This is important, so this is an important piece here to keep in mind. We're trying to maximize the volume. So because we're maximizing the volume, the first thing comes to mind is write down the form for the volume. Volume is length times width times height for a box, or some people say base times height. It's same thing. Base means the area of the base. So what I'm gonna do here, I'm gonna write down the base is 10 minus 2x times another 10 minus 2x and times the height, which is x. That gives me the volume as a function in x. I'm trying to maximize this. How do I maximize it? We are going to multiply this out first. This is 100 minus 20 plus 20, 40x plus 4x squared. And then distribute the x inside. So you get 100x minus 40x squared plus 4x to the third. So that's what we get for this one. Then v prime of x is 100 minus 80x plus 12x squared. So since I'm maximizing this, we need to find the derivative and set it equals 0. This equals to 0. Divide everything by 4 and rearrange it. So that becomes 3x squared minus 80 divided by 4 is 20x. 100 divided by 4, 25. And now let's look at this equation here. Is this one factorable? Let's try it. 3x squared is 3x and x. I see plus here and minus in the middle, so this means both should be minus. Maybe either 5 by 5 or 25 by 1. Let's try this way, test it out. Negative 15, negative 5, that's negative 20. Yes, that works. So I got two values of x. X equals 5/3 or x equals 5. So I don't know which one would minimize or maximize the volume. So how do we do this? We use the second derivative test. V double prime of x. From the first derivative, we got 0 minus 80 plus 24x. 24x. And now we're going to substitute the first point 5 over 3 in. What does that give us? Negative 80 plus 24 times 5 over 3 by 3 1 by 3 8. Negative 80 plus 20, plus 40. So that gives us negative 40. That's less than 0. What about the other one? If we try v of 5, let's see what we get. Negative 80 plus 24 times 5. What does that give us? Negative 80 plus 120. That's 40. That's bigger than 0. To maximize it, it has to concave down. Concave down means the second derivative must be less than 0. So this means we can say by the second derivative test, x equals 5 over 3 works. X equals 5 over 3 works. Then what about the other side? So this is the height. This is the height. This is the height of the box. So the other side was the length and width were the same, 10 minus 2x. So let's substitute that in 5 over 3. And what do we get for this? 10 minus 10 over 3. 30 minus 10, 20 over 3. So the dimensions are 5 over 3. Don't forget the units. The problem started with centimeters, so those will be in centimeters. 5 over 3 centimeter for the height, 20 over 3 for the length, centimeter and the width are the same. So it has a base, a square base. Those are the dimensions again. That would maximize the volume of the box. Very quick notes. The first note, you can find the volume if you need, but the question is not asking to find the volume, asking about the dimensions. But we sometimes see students finding the volume, so it is fine to find the volume of the box by substituting these values into v of x. The other thing is the second derivative test. As you could see, we applied in the first example and this example. It seems it's important to help us about concavity. Just recall it, if the second derivative of function is less than 0, it concaves down, and that gives you the maximum there, or absolute maximum. And for the second derivative less than 0, that will give us it concaves up, and therefore it will minimize it. Let's look at another example. A rectangle has its base on the x-axis and its upper vertices on the parabola given by the equation y equals 18 minus x squared. Find the maximum possible area of the rectangle. Let's see, how do you find the maximum possible area? So let's draw the diagram first. This is the parabola. If you remember how we sketched the graph, the parabola. So we draw it so we can see it as if you take x equals 0 for in the parabola, we get y equals 18. So 18 is here. It's an even function, symmetric about the y-axis. So it's gonna go like that. And we have a rectangle like this. By symmetry, if this is x, and let's say this is y. Okay, this is y. So what are we trying to find here? Find the maximum possible area. So we need to find the area. What's the area? The maximum area that we can find here. How do we start with this? To find the area, we need to find an expression for it. So what's the area of the rectangle? The area of the rectangle is length times width. The area here, the length is 2x, say, times the width is y, or vice versa. But we need to write this as a function in one variable. So I can substitute the given equation, this equation here, for y. So I get a function in x for the area, 2x times 18 minus x squared. So what do we get here? A of x equals 36x minus 2x cubed. So I multiplied it out. And why did we do this? Because now we're going to find the derivative for this. This gives me 36 minus 8x squared. We need to find the critical points or numbers, so we set it equal to 0. We get 8x squared is 36. Then we can divide by 8. This can be simplified by 4. By 4 is 9, by 4 is 2. So x is the square root of this, not plus or minus, because it's a distance. So that's 3 over the square root of 2, and good to rationalize all the time. 3 square root of 2 over 2. So we get the x value. Now how do we know if, because I got the x, I can substitute back in and get the y, but we need to make sure this is going to maximize the area. So again, a prime of x, we found it was 36 minus 8x squared. We need to find the second derivative. So that's negative 16x. Negative 16x. At x equals 3 square root of 2 over 2, what do we get? Negative 16 times 3 square root of 2 over 2. If you simplify it or not, you can see this is less than 0. So then by the second derivative test, a is maximized at this point, or this number. So how do we find the area? Well, the area, we're looking for the area. the area it was started with an expression 2x times 18 minus x squared. So what do? We just substitute a of 3 square root of 2 over 2 to find the area. 2 times 3 square root of 2 over 2 times, I'm putting in bracket, minus 3 square root of 2 over 2 all square. Some calculations here. These cancel out. 3 square root of 2. And we get 18 minus 9 times 2 over 4. So by 2, 1, by 2, 2. Let's see what we get. This stays the same. We can actually factor a 9 out. That will make it 2 minus 1/2. Easier to work with smaller numbers. 27 square root of 2, and this is 3 over 2. If you multiply it out, you get 81 square root of 2 over 2. And let's see, we had any units? I always check. Find the maximum. No units. So you can write square units or just leave it like this. So the area, the maximized area is this. That's the maximum possible area. So notice one thing, just one piece of information I'd like to point out. When I found the second derivative, sometimes on tests, students don't do the second derivative. They assume, okay, I got one x value, so that's going to maximize because the question is asking to do so. It's more safe, that's how I say it's more safe to find the second derivative or apply the second derivative test. Sometimes, as it happened here in the previous example, we get two values of x. We don't know which one unless if we use the second derivative test to tell us which one specifically, if not both or none, which ones gives us the maximum volume. So the same thing here. We found and we got only one value. That's okay. We still need to find the second derivative to confirm this will give us the maximum area. So just as a quick note here, make sure to use the second derivative test. All the time in all the questions. Let's look at the next example. This is taken from Stewart's textbook. Find an equation of the line through the point 3, 5 that cuts off the least area from the first quadrant. So to me, the first thing I always do, I read the question and understood what they're saying, and they want us to find the equation. What's the equation of the line? Okay, so it goes through 3, 5. Let's say that point is somewhere here. So there's a line that goes through this. Now some people say, why you drew it this way? Well, if you draw it up, it's not going to give you an area. It has to be an area in the first quadrant. So the area in the first quadrant is this one, the highlighted area or highlighted region. Okay, that's the one we would like to do. What we would like to find the equation that will give us the least. Least means minimum area. So they give us, the only thing they give us, that the line goes through the point 3, 5. So how do we think about this? Let's say the line intersects the y-axis at point E and the x-axis at point F. I want to minimize the area of the triangle, right? So to minimize area means I need to find derivative, find the critical numbers or the critical points. And how do we minimize this, the area? Well, to find the derivative, I need an expression for the area. So what's the area here? The area is of the triangle 1/2. Base is OF times the height OE. But I don't know, I know neither the base nor the height. So how am I gonna go about this? One thing we can do, we can use the given point 3, 5. We know that the equation of the line y minus y1 equals m the slope x minus x1. X minus x1. So here this is x1, y1. I don't know the slope, but I do know that the slope is negative because the line is going down. So y minus y1, I don't know the slope, x minus x1. We can solve for y by multiplying mx minus 3m plus 5. Okay, so that's the equation of the line. If we set x equals 0, we get y equals 5 minus 3m. This will give me this distance, the distance from here to here, that's 0 comma 3, so that's 5 minus 3m. Now I'm gonna take y0 to get the x-intercept. If y0, 0 equals mx minus 3m plus 5. So mx equals 3m minus 5. If you solve for x, divide everything by m, so 3 minus 5 over m. So this gives me the x part from here to here. That's 3 minus 5 over m. 3 minus 5 over m. So this is basically the sides OE and OF in terms of m. That's okay. That's a function of m. I'm going to go back to the definition of the area up there. So we said the area is 1/2 OE times OF, or OF times OE. So the area is 1/2 OE. OE is 5 minus 3m. 5 minus 3m. OF is 3 minus 5 over m. 3 minus 5 over m. This is a function in m, a of m. Okay, keep in mind the slope is negative because the straight line is going down, so it has a negative slope. So what we need to do to this is to find the derivative. Before we find it, you can find the derivative using product rule, or we can just multiply it first algebraically. Keep the 1/2 out, multiply this. 15 minus 25 over m minus 9m plus 15. And then this with this gives me 30. So 1/2 times 30 is 15 minus 25 over 2m. I'm multiplying the 1/2 in. 9 over 2m. That's a of m. And again, before we find the derivative, I would recommend you rewrite the middle term here, 25 over 2, and bring the m up. This way I don't have to use quotient rule. You can just use the power rule. So a prime of m equals, this is 0 minus, so that's 25 over 2, m to the negative 2 minus 9/2. This equals to 0. We said the derivative equals 0. And we need to solve for m. How do you solve for m? Keep this here, move the m squared down, and add 9 over 2 to both sides. If we cross multiply, or you multiply both sides by 2's, the 2's cancel. Cross multiply, 9m squared equals 25. How do I solve for m? M squared is 25 over 9. And what is m? M is plus or minus the square root of this by the square root property. Then m equals, I'm going to take only the negative value since m is less than 0. That's why we choose only one value. Now, if by mistake you did not pay attention to this, then you can, when we go through the next step, that will confirm the result. For example, so let's go over the, we found a prime of m. A prime of m was, what was it? Was 25 over 2m to the negative, 25 over 2m to the negative 2, and then we had minus 9/2. So I'm going to do the second derivative test, a double prime of m. A double prime of m is 25 over 2 times negative 2m to the negative 3 minus 0. So the 2's cancel out, so a double prime of m equals, a double prime of 2 of m equals negative 25, bring the m cubed down. Remember, what are we trying to do here? Let's go back up. We are trying to find the equation of the line. So to find the equation of the line, I need what? I need the point and a slope. So I have, a point was given. The point was given. All I needed to find is the slope m. So now I'm looking for the slope that would minimize the area. Make it the minimum. So how do we minimize the area? I found the area here in terms of m, and I found m. And now I'm using the second derivative test to make sure that this will minimize the area for us. So what is m? M, the one I chose was negative 5 over 3. Negative 5 over 3. Then what would be the second derivative? Negative 5 over 3. You don't have to exactly calculate it, exactly the value, but you know that the top is less than 0, the denominator is also less than 0, their division is bigger than 0. This means by the second derivative test, by the second derivative test, there is an absolute maximum when m equals -5/3. So remember again, let's say you did not pay attention to the fact m is negative. Then you will have two values, one positive 5/3 and one negative 5/3. Then in this case, when you run through the second derivative test, that would be what I call the safe tool to help me say, oh wait, this is 5/3 is gonna maximize the area, but -5/3 is gonna minimize the area. Another thing important here, and then I will finish up the problem. A lot of students, they think right away from here m is 5/3. They don't pay attention to the square root property. Square root property is very important. It says if x squared equals a positive real number m, then x is always plus or minus the square root of m. Don't forget the plus or minus. So that's important. Now to finish the problem up, remember the point we had, then it was 3, 5, and we have a slope here that we found -5/3. So then we use again y minus y1 equals the slope times x minus x1. And you can solve for y or leave it like so.